So I'm going to do one more example of the a normal approximation of the binomial. So in this particular question, we're asked, or we see, the American Journal of Public Health published a study in the mid-90s showing a relationship between passive smoking and nasal allergies. The study revealed that 65% of teenagers from heavy smoking families had indications of nasal allergies on physical examinations. A random sample of 400 American teenagers living in heavy smoking households in San Diego, 285 of them had indications of nasal allergies. So we've been given three different values here. We have this 65%. These are people who had teens that had nasal allergies. We have our sample of 400, and we have this 285. So if we were to sort of break down what each of these different pieces is, this 65% is our probability of success if we're thinking about this in a binomial setting. The 400 is our sample size, right? It's our number of trials in our binomial setting. So we have our N and our P, which is enough to answer any question. The 285, this is a particular observation from our binomial. We had 285 successes, or people with nasal allergies in this case. So this, if you really wanted to translate it into something, is an X, because we use X to denote a random variable or a count of successes from a binomial. A says, what is the distribution of X? Describing the number of teenagers who have nasal allergies. So that keyword of number telling us we're dealing with a binomial. One thing we could do is just say that X follows a binomial with an N of 400 and a P of 0.65. Right? That is one way to write this, to say, oh yeah, look, it's a binomial. I could check my bends. B, they either have nasal allergies or they don't. I, they're independent because they're randomly sampled. N, there's a fixed number. We're looking at just 400 teens. And S, that probability of success should always be the same since they're independent. It's always 65%. So definitely have a binomial experiment here. Next question says to find our mean and standard deviation. Well, we know we're dealing with a binomial, so we could go straight to our formula sheet, pull it up and go, okay, binomial, right? Mean and standard deviation, well, just pulling those straight off the sheet. So I can go ahead here, my mean is NP, my standard deviation is the square root of NPQ. N times P is just 400 times 0.65. What is our expected number of teenagers with nasal allergies? And then our standard deviation, 400, 0.65. And our Q, remember, is our probability of failure, or the opposite of our P. That's just going to be 0.35. So I'm going to go ahead, bust out my calculator, and just get us both of these values really quick. So 400 times 0.65, looks like we get out 260. And for our square root of 400 times 0.65 times 0.35, we get out 9.5394. 9.5394. Now, since we know about that normal approximation to the binomial, we actually had two correct answers when it came to what is the distribution. The second correct answer would be that X follows an approximate normal. It's not a true normal because we are just approximating, right? We saw how off our probabilities were in the previous example with that mean of 260 and that standard deviation of 9.5394. So either of these are correct. Either of these is acceptable. Normally what I do on a test is I give you a multiple choice. Either they will both be there and it's a choose all of the above, or only one is there and you just choose the one that happens to fit. So our last question says, is the San Diego result of 285 unusually high? Why or why not? Well, we didn't get a whole lot of guidance here, but we know we expected around 260 people. And what happened in San Diego is we got 285. Now, when we talk about being unusually high, we can't just look at the probability of 285 because that's going to be low by itself. We want to look at getting something like that or something higher. That's how we think of this in a statistical setting, is like, well, 285, sure enough, that could be unusual, but anything higher than 285 would be even more unusual, so we need to include those as well. We also had the ability, right, we learned in the part 2, we could just do a z-score. 285 minus that 260 divided by my standard deviation. That'll give me an idea of whether or not this is unusual straight off the bat. So we could do that. Oops. Ah, terrible things have happened. Clear 285 minus 260. Why are you doing this to me, calculator? Divided by 5.95. All right. Boom. So this z-score is around a 2.62, which is pretty close to our 3. This is looking fairly unusual. And if we wanted to get a probabilistic way of looking at it instead of just a z-score, well, then we could do normal CDF. Our lower bound of what we're interested in is at 285. Our upper bound doesn't exist because we keep going forever and ever and ever, so we throw in a crap ton of 9s, or our E99, and then we put in our mean and standard deviation that we calculated. We could have also used binomial CDF here. I'm only using normal CDF because we have the mean and standard deviation. If this were a test question and I wanted you to use the normal approximation, I have to say that. I have to say, like we did in the last question, use the normal approximation to find this. So I'm going to do a normal CDF just to see what this probability is. Sort of look at our z-score and see how crazy it is in a probability setting as opposed to just z-score. 94. Cool. Looks like our probability is 0.0043, I believe. Yes. No, 44. So, question to you guys is this unusual? You saw in the homework there's a question where us statisticians, we tend to use a cutoff of 5%. Anything that happens less than 5% of the time is unusual. And this is under 0.5%. So, very unlikely that this would have happened under usual circumstances. So yes, this is unusual. It is very unlikely. But that's essentially what we're getting at. So I'm going to leave the last exercise for us to do in class together on Tuesday before the exam.